We're on page 19. So you learned all the properties, or you should have, right? Logarithms and exponentials. And now it comes down to applying those properties and those rules, okay? We're going to do something called exponential growth and decay. Have you ever heard of that before? What does exponential growth mean? It grows at an exponential rate. So like 2 to the x, right? It's going to get bigger and bigger. The exponent has the variable, the base has some constant, right? So like 3 to the x, so on. And what's decay? It's going to get smaller and smaller. Good. So if we have here f of x equals a e to the kt, where k, that's our constant representing the rate of continuous growth. When we have k being negative, or a negative in front of k, that's going to represent exponential decay. So that's how you know the difference between the two. Growth has a positive exponent. Decay is going to have a negative exponent. It's going to get smaller and smaller. Think about that for a minute. What happens when we have a negative exponent? Let's say, just kind of on the side here, what happens when we have 2 to the negative x? Can you think of another way? How could we rewrite that?
1 over 2 to the x.
1 over 2 to the x. So what happens when I start plugging in values for x? So let's say x is 1. I get 1/2. What happens when x is 2? 1/4. So it gets smaller. What happens when x is 3? Right, 1/8. So you can see as we have a negative exponent, because we know we can switch that, what happens is the denominator is going to get bigger and bigger and bigger, which makes the actual number smaller and smaller and smaller. Make sense? Okay. So this gets smaller. We got music. So much louder next door, actually.
Oh, really?
It is. It's louder next door. Okay, so here's some formats for continuous growth or decay. So you're going to see two different formulas, and I'm going to tell you they're essentially the same thing. We have A equals P e to the RT. Sometimes people call that A PERT. It just helps you to remember the order. And then we have Y equals A e to the KT. These are actually the same formula. We just use different letters for population versus any kind of, usually we use this for money, like loans or things like that. So this is money. And this is population growth. Now, it could be anything in terms of population. It could be referring to actual population of people. We'll see later on it could be other types of things that are growing or decaying. But I will say, for now, population. Now, here we have a couple of variables. We have P is the initial amount. So that we always think of, this is what we're starting with. A, what's A? That's the amount at time t. So usually this is the result. This is what we end up with, okay?
So like after time.
Yeah, exactly. So now sometimes we actually know what we end up with, but we don't know what we start with. And that's where we use our logarithms and our exponents, you know, those properties and solve. And then R is always going to be our interest rate. Okay. Again, this is for continuous compounding. So it's constantly growing. For population, we're going to use A as our initial population. So same thing, right? It's like this is what we start with. And then we have Y. That's the population at time t, so that's what we end up with. And then instead of R, we just use the letter K for continuous growth. So R and K are both rates. Now we want to make sure whenever we're working with R and K, we're always working with decimals. Okay. So if we have R and K, they must be in decimal form. So if I give you 4%, you're going to write that as 0.04. Good. Next, carbon dating. So have we heard of carbon dating before? So what does anybody know what carbon dating does? How long something has been on Earth. So the amount of carbon that's in certain materials is going to decay over time. So that's how you can figure out like how old a fossil is, or how old, you know, certain formations are, or even artifacts. You can figure out by the amount of carbon that maybe it's, you know, that it started with and how much it ended up with to determine how old that is. So carbon-14 has a half-life, and it says right here, carbon-14 has a half-life of 5,730 years. So what that means is the amount of carbon, let's say you start with 100 grams of carbon. After 5,730 years, how much do you think you have? If you have 100 grams and the half-life,
50.
you end up with 50. So it takes 5,730 years for the amount of carbon to be cut in half. So then if you have 50 grams, so then another 5,730 years later, how many grams of carbon do you have? 25. And then another 5,730. So that's how you can date things like fossils, okay? So let's talk about carbon life and its rate. So we want to use the formula, even though it's for population growth, we use basically the A equals PE to the RT for money. Anything else, we're going to use this formula. Okay, so let's write down the formula first. We have Y equals A E to the KT. And we want to find out what is the value of K. Well, it seems like we don't have enough information, right? But we do. So what was I just telling you about the 100 grams and then the 50 grams? It's always going to be cut in half, right? So I'm basically going to have half of A. So think if I start with A, we end with 1/2 A. Does that make sense? So if A is my starting amount, I'm always going to have half as much as I started with. It doesn't matter if we started with 100 grams or 1,000 grams or what that amount is, and you'll see in a moment. Yes?
Isn't the 5,730, isn't that the half, so wouldn't you just multiply
Well,
it?
actually, that is going to be the number of years. This, right, 5,730 years, this is the amount of time that it takes to reduce to half of what it started with. So we're going to use that amount here. Okay, you see what I'm saying? So we don't know what the rate of the half-life is. That's what we're trying to solve for. But we know the amount of time it takes to reduce to half. So is everyone okay with how I plug that in?
Yeah.
Okay. Yeah? Good? Well, what can I do first? Notice I have A on both sides. Yeah, I can divide both sides by A. So I get 1/2 equals E, and I'm just going to put the 5,730 in front of the K, just so it looks like a coefficient. All right, we're good now because we only have one variable, right? E, what's E approximately?
2.17.
2.7718, so it just switched around. That's
Wait, how
okay.
did you know that? Where did that come from? Oh, right. Oh,
Good. Yeah, you just learned it, right?
Yeah.
Because E is Euler's number. It's the base of the natural logarithm, okay? And E is used in lots of like real world application, and that's what we get to see here. So E is some constant we don't really need to worry about what it is. What we're trying to do is we're trying to solve for k. Now, you did solving already.
Yeah.
What do we do to get the variable out of the exponent?
You
Or-
get the natural.
Good, so we're gonna do natural log of a half, and I'm gonna do natural log of e to the 5,730k. Well, what happens now? Yeah, so I have natural log of 1/2 here, but I end up with just what on the right side? 5,730k. All right, we're almost there, right? What do we do to solve for k? Divide. Perfect. Okay, now we're going to pick up our calculators. So I put in natural log of 0.5, and we're going to divide by 5,730. And we get a really small number. You ever notice how we get that e? What does e mean when you get it on? So that's times 10 to the negative 4 power. So I'm going to just, I'm not sure how many decimals she wants. The 10,000th place.
Yeah, but it's like.
So, but now it's going to be even smaller. You want to,
She did too.
what did did you get to this one yesterday?
We did one like that though.
Oh, okay. So what, tell me, it was negative 0.123 or 3 zeros after, and then it was 1, 2. Did you go further than that?
No,
Or did you write it differently?
no, we
No, we
wrote
wrote
it
it
as
different.
negative 1.21 because it times by the other.
Oh, you did write it that way. Okay. So negative 1.21 times 10 to the negative 4. Perfect. Okay, question, yes.
Why do E and Ln cancel each other?
So the natural log has a little base e here that we don't write. Natural log is a logarithm with a base e. Well, what happens when my base, when this and this are equal to each other? Like, remember when you did logarithms and you had log base 2 of 2? You get 1. So what happens when you have, you see, there's really a little invisible e that you can't see there. Anytime you see natural log, think, oh, there's a little e that we don't write down. We assume that it's there so that when I do solving equations with these, I know there's a little e here. So that's how we know they cancel. Anything else? Any other questions? Okay, not so bad, right? Okay, half-life of sodium 22 is 2.6 years. We want to determine the K value and the equation of decay. So I'm going to go back to my equation, y equals a e to the kt. So let's identify what's going on here. Again, we're working with half-life, so it's going to look very similar to the previous problem, but what's different here? The what? T is now 2.6. So 2.6, that's T. Now again, I didn't give you any actual amount. We just said the half-life. So how would we start this? Okay, so half A equals A, E, and then I have 2.6 times K. I'm just going to cancel out my A's because same thing's going to happen like the last one. So we have 1/2 E to the 2.6 K. Good, so we're going to do natural log again of both sides.
Why would you just be negative k though? Because it's the k.
So what ends up happening, oops. Let me ask you a question about natural log of 1/2. Is there another way that you could write natural log of 1/2? How about natural log of 1 minus natural log of 2? Right? You just learned all those properties about switching from, right, division, expanding, and also condensing. Are we okay with that? What's natural log of 1? Did you learn that property yesterday? It's 0. So notice I get a negative here. So whenever I do half-life, yes, I'm going to get a negative answer because half-life is decay. It's saying you're starting with a certain amount and it's getting smaller and smaller and smaller. So that rate will always end up being negative with half-life. Okay, that's actually a good way to check your answer. If you end up with a positive number, you know you did something wrong for K, because K should always be negative for half-life.
So does it matter if they're asking for growth or decay?
Sometimes they might not tell you. Usually they'll, something like this with half-life, it's always decay. But sometimes with like a certain population, there are problems. I know next year you'll do in pre-calc or the trig class that you talk about things that are like population usually gets bigger, right? So in those cases, K would end up being positive. Does that make sense? Yeah. So here we have natural log of a half. What happens on the right side? We get 2.6K, and we're going to divide both sides by 2.6. So I get, let's plug that in. Oops. So I have natural log of 0.5. Always make sure you close your parentheses after you put the natural log in. Now we get divided by 2.6. So again, remind me, how many decimals does she want? So negative 0.2666. Now that's just the first part of that question. It says determine the K value, and now I want to write the equation of decay. Now keep in mind, it was AE to the KT. I don't know what Y is. That's my result. I don't know what A is. That's my starting amount. But I now know K is negative 0.2666. And I'm going to put T. I'm not going to put 2.6. What I want to do is take that equation and only plug in what we know. We only know K.
We also say 0.1 Y. Like apply the 10% to the answer.
Well, we're going to actually apply that down here for part B. Yeah. This is okay, so basically what we want for a problem like this is we want to be able to solve this now for any amount. So maybe I'll say, oh, what's the amount after, let's say I start with 20 grams. Start with 20 grams. How much do I have after 5 years? So I'm able to plug in because that equation is going to relate all of those variables. Does that make sense? Mm-hmm. Or what if I know I had 30 grams, I started out with 10, how long did it take me to get there? That's solving for T. So that's a different type of problem. Now we're going to actually apply that for part B. So a geologist examining a meteorite estimates that it contains about 10% as much sodium-22 as it would have when it reached Earth's surface. So how long ago did the meteorite reach Earth? So I'm going to just rewrite this again. When in doubt, just write down the formula. So we're using that equation from the previous problem. Now, what do we want to find here? How long ago? So we're basically, right, how long ago we have to figure out what T equals. So that means we must have enough information relating A and Y. Do we? Okay, what do we know? That it contains about 10% as it would have when it reached the Earth's surface. Now, we don't have an actual amount, just like we didn't have an amount with half-life. So what are we saying? We're saying there's 10% result from what we started with. So we're going to put 0.1 A, actually. Why do I put 0.1 times A? Well, A is when it actually reached the Earth. That was the starting amount. It's 10% of what I started with. Does that make sense?
Oh, right.
You know, and again, if you had switched the numbers around or switched the place, what would end up happening is you'd get a positive K, and then you know you made a mistake because this is getting smaller. This is a decay. All right, does that make sense? So these are nice problems too because you can kind of check your answer. So 10% as much as you started with. Are we good? Okay, so what do we do with the A's?
They cancel.
Yep, they cancel right out, so I'm just going to cross those out. So we have 0.1 equals e to the negative 0.2666t. Good. Okay, go ahead and do that. Does anybody want to? Get me the answer.
Yeah, 8.6369.
8.6369 for t. And because when we first originally looked at the problem, this is measured in years, so we would say 8.369 years.
Wait,
What's that? Did I switch something? What's wrong? Are we okay?
You have like a 0.6369 a year.
That is okay. We could always change things to, so in math, like you're gonna have to just round, I don't know exactly, like if she says 4 decimal places, just always round to 4 decimal places, even if it doesn't make sense in terms of years. You could actually change this. Like you know what half a year is? What's half a year? Right? It's 6 months. So you could always change a decimal of a year in terms of how many months and weeks or whatever that might be. Okay, questions? Good? All right, I think this is the last 2 examples, okay? All right, 2007, population of China was 1.32 billion. In the year 2000, it was 1.26 billion. So determine the K value for China's population growth. Let's write down the formula.
Wait, isn't the other one?
No, it's not money.
It's not money, so we're not going to use the A per one. Remember, anytime you see dollar signs, think you're going to use the A per A equals PE to the RT. Population, we're going to, population, anything else falls under the category for this formula, okay? All right. We have to figure out K. What do we know? Well, do we know the starting amount?
Yeah.
Yeah, what was the starting amount? Good, so this is what we start with. This is our A. Do we know how much we end up with? Yes. Good, so 1.32 billion, that's our Y. Do we know T? Okay, how many years have passed? Yeah, from 2000 to 2007 means that Y, or sorry, not Y, T. T equals 7. Great. Let's plug everything in. We have 1.32 equals 1.26 e to the 7k. Now, is my k value going to be positive or negative?
Positive.
Definitely positive because it's getting bigger. So if we get a negative, then we know we switch something around. So I don't, it doesn't cancel nicely like the ones before where you had A on both sides. But we're really using the same process. So yeah, we're going to divide both sides by 1.26. Now I'm not sure if that works out very nicely. Let's see, 1.32 divided by 1.26. So let's round that to 4 decimal places, which would be 1. Good. And that's going to be equal to 7, or sorry, e to the 7k. But the next process is going to be the same. What are we going to do to both sides? Natural log. So natural log of 1.0476 equals natural log of e to the 7k. So that's going to bring down our 7k. Divide both sides by 7. Anybody get that yet?
Yeah.
Is it
0.0066.
0.0066? Excellent. So we ended up with a positive number, which is good because we can definitely see the population's getting bigger. Yeah.
Will we have to put zeros for the billions because it's in the billions or no? Or just leave it 1.0?
Oh, you mean for part B? Or which part?
No, I'm saying like because it was 1.32 and 1.26. Wouldn't you have to put zeros after that because it's in the billions, or just leave it as a
Well, you know, when we actually solve for this,
It wouldn't matter.
yeah, because notice the next, the zeros would end up canceling out anyway. And in fact, when we apply the next example, it already has it in billions. Now, what if they didn't put billion and they put the actual zeros? Then we'd either have to change it to, the decimal and then write billion. So you just want to make sure that it matches like the units, however that looks. Okay, so when will China's population reach 1.5 billion? Well, we have y equals AE to the KT, right? And we found out what? Well, I know what A is. I know my starting amount is 1.26. We have E. Now we know K. We're looking for T. And this, actually, I'm going to erase my Y because that's actually my new result. I want to find out how long it takes to reach that. So that's going to be my new.
You don't use like the most recent popular number.
You can, actually. You can.
Because like it wouldn't answer you yet if you got like say it was like 5 years, wouldn't that be wrong?
Well,
because you started at like when it was the year 2000.
You would have to, you can actually use the 1.32. You would just need to think, okay, well, when I solve for T, that's going to say the number of years after 2007. Does that make sense? Whereas now, and I'm solving for, when I use 1.26, when I solve for T, this will give us,
So you end up in the same year. Just get a big number or smaller.
it'll be the number of years after 2000. If I use 1.32, that's going to give me when I solve for T, that's going to give me the number of years after 2007. So it all depends on what your starting point you use.
So on a test, you think you just accept both?
They're both correct, and you should get the same answer for both of them.
You just do like 2000 plus whatever.
Exactly. You would do 2000 plus whatever you get for T for this one, but if you use 1.32, you would do 2007 plus whatever you get for T. Yeah, you should get the same answer. Maybe you want to give that a try. So here, I'm going to divide both sides by 1.26. Anybody have the decimal that you get on the left side?
1905.
1905. Good. So we take natural log of both sides. So we're going to divide both sides by that decimal. What do we get for T?
26.4202.
26.4202? Okay, now it says when. So that means 2,000 years plus that amount. Does that make sense?
So 2000.
So it starts out in the year 2000, and if we add that,
2026.
so it's going to be somewhere in the year 2000. Yeah, you could say, and you're going to have to clarify with her. You might want to check with
She told
maybe
us to round to like whole numbers
if it's for years.
if it's like something that
Okay.
should be whole numbers.
Okay. So it's going to be sometime around the year 2026 or 2027 because it's in between those. I assume she'll probably clarify, like on a test or a quiz. So if you think so somewhere in the year 2026. Okay. Any questions on that?